Hi there, this is Penelope. This is a short video on circular definitions of trig functions. And the question is, why? Why do we talk about these trig things as being circular functions? We've looked at triangles, right-angled triangles, and we've found the sine and the cosine and the tangent of an angle, or we've used the inverse of those to find the angle itself. But we need a little bit more. If we're going to be able to draw the graphs of these things that we call sine theta or cosine theta, then we have to regard the ratios not just as a single ratio, but we need to regard them as some sort of continuum of changing angle values. We need to therefore actually think of these trig ratios in the sense of a function. Now, what we do is we put that right-angled triangle into a circle, but to make things easy for ourselves for the calculations, we make the radius of that circle 1 unit. And what we can do then is we can trace out every single angle right round from 0 to 360 by moving the arm, the radius of that circle right round the 360. Now we know that cosine of t is equal to the adjacent over the hypotenuse, and in this case it's the x and the hypotenuse is 1, so the cosine of whatever angle we're up to is just the horizontal measurement, and the sine of t is equal to the opposite over the hypotenuse, which is y, and again our hypotenuse is 1, so it's the vertical measure. So we could just take a ruler and measure that, possibly not very accurately, but we could. Now, when you do this for the common angles, what you get are the ratios that we looked at in class 1. So what we've got here is, if I was to drop a right angle line down from, say, sine 30, like that, and then looking for sine 30, we know it's going to be the opposite over the hypotenuse. Now again, just a unit circle, so it's the opposite over 1, or just plain the opposite length, and taking a ruler or even just eyeballing that, it looks like it's a half or 0.5, because remember it only goes up to 1 at the maximum, it only goes up to 1, and then this is about half. It is half. If we're looking for the cosine of 30 degrees, it's the adjacent over the hypotenuse, which is the adjacent over 1, or just plain the adjacent for the unit circle, right? It's for the unit circle. And again, if we were to measure that, it would be about 0.866. Now, if you were using the triangles that we did in class 1, then you'd also know that that was root 3 over 2. So whether you're using a ruler very carefully, or whether you have memorized the ones from the previous class or 2 previous classes ago, that's the value. And you can do it for any angle. You don't just have to do it for the common ones. You can do it for all of the angles, even tiny little bits of angles. And that's how it's worked out. Now, I'm not going to show this link because it really has got awful music, but you can do a Google search on animated sine curve or animated cos curve, and you can see then how moving the hypotenuse of your triangle around the circle actually traces out a sine curve or a cos curve, whatever it is that you're looking at. Now, just got a wee screenshot from one of those animations. So if we look at this, this is This is a sine curve. And what I've captured here is my angle is something a little bit less than 4 pi over 3. Doesn't matter exactly what it is, but if we go round at that side, then we've got a length. So we're looking for the vertical length, or the vertical distance. Because it's the y measure, then this length here is the same as that length there. And then you can imagine that line continues on around the circle, and it gets a little bit longer, till it's 1, and then it starts to get shorter again, and all the preceding little right angle triangles are what drew out, that vertical length is what drew out the green line. Every angle, even 0.001 of an angle, can be found, the sine of it or the cosine for the other graph can be found by using the same analysis. Okay, thanks for watching.